So chapter 7 is trig identities and equations. We get to do our proving of the identities. That's going to be really exciting. So that's our identities. And then equations we're going to be solving. So we're going to be solving a bunch of trig equations. For 7.1, we're just looking at what an equivalent trig function is. Just a little bit of an exploration of some different ones that we haven't talked about before, or we have looked at before, and we're just going to highlight little characteristics. So there's a little bit of equivalent work here. So a lot of this lesson today is going to be about just what's equivalent to each other. I'm going to picture it in graphs. So some of these I'm going to draw. Some people just memorize things. I like to picture them. So we're going to talk about a lot of equivalent. So equivalent. And this equivalent is going to lead us to the identities that we're going to use, right? So when we prove an identity, we're using equivalent forms. When we substitute something in, we're using an equivalent form to prove the identity. So that's what the equivalent section is about. We're looking at what's equivalent, and it's kind of leading towards the identities that we're going to be doing later on in the chapter. And we also need equivalent when we're solving equations, because we're going to do substitution in order to solve it. Okay, so that's why. So this is just a nice warm-up section. So equivalent, there are equivalent trig expressions since a trig function is periodic. We know it's repeating itself. So when it repeats itself, we're going to be able to get more than one answer. So when you look at something, you go, okay, when is sine of theta equal to the same amount? We know that because, for example, right? Because it's periodic, we're getting equivalent expressions. So we're going to get equivalent answers throughout. Right? Does that make sense? These are all the same answer. We're going to get the same answer, same. So equivalent expressions. So equivalent, because they're periodic, they repeat themselves. We're going to get more than one answer. You can use a graph or translations or the unit circle, because we know it repeats itself on the cast rule, to visualize equivalent expressions. So the unit circle is where we develop the cast rule, right? So we know it repeats and repeats. Graph is over here, where we're going to use a graph, and we can use that to visualize equivalent expressions. Like I said, I tend to visualize it versus memorize, right? So there's things where you can memorize the formula. I tend to visualize based on cast rule and the graphs, and then I can kind of see why they're equivalent, why they're the same. Period. The period of a graph is where it repeats itself. So a period is going to help us find equivalent expressions because it repeats itself. You're going to use multiples of the period to get an equivalent fraction. So that means that if we know that the period for the sine and cosine, we know that their period is 2 pi. True for sine and cosine? Right, for the regular? Yeah. Okay, for the sine and cosine, it's 2 pi. So that means I can add 2 pi to any answer to get to my next answer. Right? So I can add 2 pi to any answer to get to my next answer. What does that mean? So let's look at degrees. So if I said to you sine of 20 degrees, I could say that that's the same thing as sine of, I'm going to add the period. What's the period for a sine function in degrees? 360, right? So I'm going to add 360. So this would be the same thing as sine of 380. Does that make sense? 380. So sine of 20 is a sine of 380. It doesn't have to be in a bracket. I'm just emphasizing. So sine, what if I added another 360 to it? Can I do that? How about if I add 720? It's 2 periods. So I'm going to hop over twice, and I could do that. So that would get me another of the same answer. So these are all the same. So trying it on my calculator, if I did sine of 20, that's, oh, I'm in radians. I'm going to switch my mode to degrees. So if I did sine of 20, I get 0.342, blah, blah, blah. If I did sine of 380, oh, it's the exact same thing. Right? So that's what it's saying, is that any multiple of the period, I can do 2 of it, I can do 10 of that period. What about backwards? So can I minus 360? That would be the same thing as sine of negative 340. So what if I did sine of negative 340? Oh, it's exactly the same number. So these are equivalent, right? So when I add the period to it, I'm cycling around and getting exactly the same. It's not the same. Yeah. Okay? I'm getting exactly the same answer. So that's equivalent. They're all the same because I'm adding 2 pi to it, which is the same thing as adding 360 to a degree, right? Or subtracting. Add, subtract. Same answer. So that's like saying here, if I got my answer here, if I added 3 pi to it, I would get my answer, or 2 pi to it, I'd get my answer here. I add another 2 pi, I'd get my next answer. So adding 2 pi to it gets you the next dot on the graph. And it's periodic, so you can go backwards or forwards. Does that make sense? So the period. So I can add 2 pi or subtract. So it'll be any multiple. So any multiple of the period. So plus 2 pi, minus 2 pi, etc. Right? So any multiple can be positive or negative. You're going back and forth. And does the period always have to be 2 pi? No. Right? So then we can go into the fact that maybe the period is not 2 pi. It's of the period. So if the period was pi, then I would add pi to it to get the next set of answers. We're going to use this when we're solving our equations. So when we solve our equation, we're going to get our first set of answers, and then we're going to say, but it repeats. So then it goes again and again and again and again. So we're going to use this idea of period when we're solving our equations. Okay, when we're solving for the angle. Okay, so we'll come back to that again, right? So that's a very good thing to know, that it repeats and repeats. Now, the next thing. So that's a thing to know. We're going to use that. Horizontal translation. So sometimes I'm going to ask you, are these equivalent? Or how can I simplify this? Is there a simpler way to write it? Pi over 2 is a nice translation. So in terms of horizontal translations, I'm going to graph them. So I'm going to graph both sine and cosine on the same grid, and we'll see that they're translations of each other. You already instinctually know this, right? Because we've graphed so many of them. They're exactly the same graph. So we know they're the same graph. So if this is y, sorry, and I should have been labeling this theta. I've been labeling it x, but it is theta. If I use theta there, it should have been theta. I realize that in my other graphs. I don't mind if you put x there. I just, on the graph, when it's on the equation, I realized it says theta. I should have been putting theta, not that. Someone asked me that. And I'm like, yes, I have been putting x on all the stuff. So thank you for pointing that out. But yeah, and if you did put x, it's okay. I mean, the other teachers, we checked and we went, shoot, we're all making that same mistake. We're putting x, but it should have been theta. So thank you. So if I'm doing this, I'm just going to graph it, just one period, just so I can demonstrate what it looks like, and I'll do one here. And again, just so I can show you the translation. So we're looking here at these two, sine and cosine, and we're looking at horizontal translations. So horizontal translation, we're using that to write an equivalent expression. So this whole section 7.1 is looking at ways to write things equivalent. And I always think of it as like, is there a way I can simplify it, right? We're trying to simplify it. So it's horizontal translations, and we're looking at simplify. So I'm going to look at sine first. So I'm going to graph sine first, and then we're going to compare the two. So sine starts here. This is 2 pi, goes up, down, down, up. Try to make it look like a half circle, right, or a parabola. And then another parabola that goes like this. Okay, so that is sine, so that is y equals sine theta. So I'll do that in green here. Then I'm going to do, and I'll do this one in pink. So I'm going to do the cosine one in my hot pink here. So we're going to do cosine starts at 1, heads down. And this is y equals cos theta. So I have my two graphs. These are equivalent expressions if you translate them. So again, they're just trying to get you used to the idea of equivalent, which I always think of is like simplifying. So can I simplify this to be a cosine and a sine? Yes, you can go back and forth. So if I have the cosine graph, I can make it into the sine graph by translating it. That would be right pi over 2. Does that make sense? So that's pi over 2. So a cosine is actually the same as equivalent to the sine graph if I moved it right pi over 2. That's what this is saying. The sine and the cosine would be the same if I moved the cosine right pi over 2. Then this one is saying, oh, you know what? You're right. But also, I could move my sine graph, the green one, I could move it left pi over 2. I could move this top here, put left, and then it makes it cosine. So these are both equivalent expressions. So I can make a sine into a cosine graph, or a cosine graph into a sine graph by shifting it by a horizontal translation of pi over 2. And it's an equivalent expression. That makes sense, equivalent? So equivalent just means make it equal, and we can use translations to do that. Okay. So that's not really something to memorize. It's kind of just something like, oh, if I needed to know, are they the same? Yes, they are, and I usually graph it. Right? So no need to memorize, just understand the graph. It's a horizontal translation one way or the other. Any questions with that? And again, you should label that theta. I'm sorry, I've been labeling it x the whole way through. So try, I won't mark it wrong if you mark it x. Again, that seems to be my typical mistake. I'll try to do it better now. If you have the variable theta, it should have been theta. Nope, that's me. Okay, here we go. Good for that one. I'm going to move up. So that's just horizontal translations. Now, they're going to talk about even and odd. We haven't talked about this for a little while now, right? So it's been a minute, so we're going to talk about even. An even function, and we'll talk about odd on the next page. An even function is a function that has the horizontal reflection, right? So if I horizontally reflect it, it equals the same thing. So that's this. That's this statement. You do not need to memorize any of this. You're just trying to picture the graph. So if I give you cos of negative or cos of negative theta, you're going to go, but that didn't do anything. So usually what happens with this is that if I give you the cos function, you can do any domain you want. I'll just do the same just so we can picture it. I don't need to do anything else. If I did the cos function, if I gave you the cos function and I put a negative in the bracket, we know that that negative means, that negative here would mean horizontal reflection. Does that make sense? So in my brain, I'm thinking that that negative means horizontal reflection, which means that my cos graph is actually drawn this way, horizontally reflected, so it would go backwards. So it's on this side. Like that. Right? So it's the cosine graph, but horizontally reflected, so this is right here. So that's what I'm showing you there. But it's periodic. So it keeps going. Make sense? Okay. So it keeps going like that. And then you go, wait, but if I can make it keep going on the other side, isn't that the same thing as cos theta? So then my negative, so this here, cos of negative theta, is actually equivalent to, so that's why they say they're equal to, because these two end up being equal to each other. So cos of negative theta, which is the pink one, and cos of theta, which is the orange, these two are equal. And that's what they mean by equivalent. Right? So a horizontal reflection in cosine is actually cos theta. So if I gave you cos of negative theta, you would go, oh, but that's cos of theta. It's equivalent to it. So it's like simplifying. Right? What's a simpler way to write this? Just write it as cos theta. They're equivalent. And again, I don't memorize it, I picture it. So if I give you this, you go, oh wait, it is the same thing as this, because if I extend it. Right? So that's equivalent. Yeah. Questions with that? All right, so flip over. Okay, we're going to do odd and then talk about that, and then we'll do some other stuff. So, good. All right, so let's talk about odd. Odd we did before, and odd, when we had to prove odd, we would make that the horizontal and the vertical reflection were equal, or you did a double flip. You did a horizontal and vertical to make it go back to the beginning. We're not proving that they're odd or even, right? So we're not proving that. They're saying that these two are odd. They're rotated about the origin. We're going to use it here. This is where it's interesting, is that what ends up, and again, you don't have to remember the definition of odd and even. What you're going to remember is this stuff. So if I reflect a sine graph vertically and horizontally, I'm going to get the same answer, right? So it's not the definition. So I don't need you to go back and memorize odd and even. It's this part, the algebra of it. So if I give you, so I'm just going to draw a little graph of sine and a little graph of tan here. So this will be for my sine graph, just to show you that a vertical reflection and a horizontal reflection are going to be the same. And I think you know that anyway, kind of when you picture the graph, you go, oh, I get that. So I'm just going to do one. I'll just do 1, 2, 3, 4. I made it mini. I made a mini graph, teeny tiny, because I just wanted to show you that they're the same. So let me draw. So the first one I'm going to draw is I'm going to draw this one, which is sine with a negative in the theta, which means horizontal reflection. Is that okay? So horizontal reflection for this one, horizontal reflection. So I'm going to draw that one here. So normally it's this way, and I'm going to reflect it, and it's going to go backwards. So horizontal reflection. Right? Horizontal reflection means I took the graph and I reflected it horizontally. Is this okay? So this one is sine of negative theta. Y equals. Is that okay? So I reflected it there. I just want to show you that they're equivalent. Okay. Then for this one, I'm going to draw on this right side. I'll do this one in pink. It's a vertical reflection. So we know that the graph normally goes up and down. I'm going to have it facing down and up. So this is y equals negative sine of theta on that side. Are they the same? Yes, so that's why they're saying, hey, they're equivalent. These are equivalent expressions. So equal, equal. Okay, so it's not memorizing, is that sometimes we will use the graphs in order to go, oh, wait, a horizontal reflection is actually a vertical reflection. A vertical is actually a horizontal. So we're going to use that when we're simplifying. When we're proving identities, maybe when we're solving, we'll use an equivalent expression. Good? So equivalent. Let's do the same thing with the tan graph. I should have moved this over a little, right? The tan graph is more of a pain in the neck to draw because it's just got so many, but let's just want like 1 or 2 little cycles. Okay, and again, I just want to show you, so let's do one cycle here where we get up to the asymptote. Okay. Where's my first asymptote for the tan graph? What would this be? When cos equals 0, where's cos equals 0? Pi over 2, okay?